Welcome back to this next video in which we are discussing fields and ideals. Okay, so we've now seen that if you have a field, it has only two ideals, namely the zero ideal and the unit ideal. We've also seen that if you have a commutative ring that has only two ideals, the zero ideal and the unit ideal, then you can conclude instantly that that commutative ring is a field. Okay, right. So what we're now going to do is we're going to look at another related theorem about fields in the theory of ideals, namely that all of the ideals in the ring of polynomials over a field are principal ideals. Okay, so let me put this here. So, what we're going to be considering then is the ring of polynomials over a field, which we will denote like so, f square brackets x. Okay, so this, remember, is the set containing all polynomials where the coefficients are in the field capital F, and the way that we add and multiply these polynomials is the normal intuitive way for adding and multiplying polynomials. Namely, you add the components in front of each of the powers of x, and you multiply polynomials by splitting polynomials into their monomial decomposition, so thinking of a polynomial as the sum of lots of monomials, and then multiplying the two polynomials by multiplying every single possible combination of the monomials together, and then adding all of the answers together. And the way you multiply monomials is just by multiplying the two coefficients in between them, in front of them, and then adding the powers of x. Okay, so there is our ring of polynomials over the field capital F. What I now want to show is that if I have an ideal, which I'll call capital I, which is an ideal of the ring of polynomials over the field capital F, that this is in fact going to be a principal ideal. So I want to show that any ideal is a principal ideal. It is a principal ideal generated by some polynomial. Okay, so I can write it like so. The principal ideal generated by some polynomial p of x, i.e. it's going to be a subset of the form a polynomial f of x times this polynomial p of x, where f of x here is an element of the ring of polynomials over the field capital F. Okay, so this is what this ideal is going to look like. It's going to be a principal ideal generated by some polynomial p of x. So I want to prove that any ideal in a ring of polynomials over the field capital F is going to have this form. It's going to be a principal ideal generated by some polynomial in that ideal. Okay, so how then am I going to go about proving this? Well, before we actually begin, let's just explore ideals in the ring of polynomials over the field F in a little bit more detail. So let's draw a picture here. Okay, so let's let this box represent our ring of polynomials over the field F here, so f square brackets x. So we'll denote this in orange, like so. Okay, so let's think about ideals in here. So firstly, of course, one of the ideals that we can always conclude will be there is the zero ideal, which will just contain the zero polynomial, which is where you have zero, the additive identity from the field, in front of every single power of x. So it's a really boring polynomial and it's just denoted zero. So of course that will be an ideal, the subset that just contains zero. Now, if you consider principal ideals generated by polynomials which just have a non-zero coefficient in front of the x to the power of 0 term, so the constant polynomial. So let's say we have some constant polynomial here. I might actually just denote it, no, not x. I shouldn't denote it x because I'm using x as the indeterminate here. So I'll just denote it r. So r is some element of the field capital F. So if you have some constant polynomial here where the only coefficient that is non-zero is the one that's in front of x to the power of 0, then if we generate the principal ideal generated by that, what will that ideal look like? Well, I claim it will actually be the entire polynomial ring here, and the reason is that this r here it's a non-additive identity element of the field, so it will actually have a multiplicative inverse in the ring of polynomials over the field F, namely the multiplicative inverse in the field, so 1 over r. So now look at the polynomial, which again is a constant polynomial, and it's just 1 over r. Then I claim these two polynomials will multiply together to give the multiplicative identity 1. Okay, so the multiplicative identity in my ring of polynomials over the field F. And of course we know that whenever you have the multiplicative identity in your ideal, you instantly have the entire ring in your ideal. Okay, so if you generate the principal ideal generated by a constant polynomial, either it's the zero polynomial and therefore you'll get the zero ideal, or if it's not the zero polynomial but it is still a constant polynomial, you'll get the unit ideal, you'll get the entire ring as your ideal. Okay, but then if you take polynomials which are a little bit larger, so they actually have non-zero coefficients in front of powers of x above x to the power of 0, then those will generate more interesting ideals. Okay, so that's just a little bit more insight into ideals in this ring of polynomials over the field F. So let's now go back to our theorem. We are trying to prove that any ideal is a principal ideal generated by some polynomial in this ring of polynomials. Okay, so how am I going to go about this? So let's say I have my ideal. Okay, and I'll draw a fresh picture for this. Okay, so here is my ring of polynomials f square brackets x, and let's say I've got my ideal, which is this subset here. Okay, and once again I'll just colour this in, so we'll have the ring of polynomials over the field f in orange here, and then we've got the ideal here, which I'll have in green. Okay, so how am I going to prove this then? Well, what I'm going to first start off by is asking which polynomial would you suspect is the one that is actually going to generate the entire ideal. Okay, so I'm trying to write the ideal as a principal ideal generated by some polynomial. Now of course when you generate the principal ideal of some polynomial, that polynomial will be in the ideal, so it's got to be some polynomial in the ideal. Okay, now which polynomial would you expect it to be? Well, you would expect it to be the polynomial of smallest degree, because if it wasn't the polynomial of smallest degree, then how would you actually get polynomials of smaller degree in this principal ideal? Okay, because this can only raise the degree, right? Multiplying it by f of x, apart from multiplying it by the zero polynomial, of course, but except the zero polynomial, whatever you multiply it by will raise the degree of the polynomial here. Okay, so you would expect that if you're going to cover the entire ideal here, that this would have to be the polynomial of smallest degree apart from the zero polynomial. Okay, so we don't even give the zero polynomial a degree. Remember, the degree of a polynomial is the highest power of x that the polynomial has a non-zero coefficient in front of. So constant polynomials have degree 0. Polynomials where the highest power of x is x to the power of 1 will be degree 1. The zero polynomial has no coefficients which are non-zero. Okay, so it can't really even be ascribed a degree. So, you find the polynomial which has the lowest degree then in your ideal. Now obviously either your ideal will be the zero ideal, in which case you won't be able to do this, or it will contain at least one polynomial which isn't the zero polynomial, and then you'll be able to find the polynomial of smallest degree. Okay, so you find the polynomial of smallest degree, and I claim that it's this polynomial p of x of smallest degree that is actually going to be the polynomial which we can use to generate the entire ideal. Okay, so once you've found this polynomial of smallest degree, which must exist in there, okay, there must be some polynomial of smallest degree. Now of course, there might be loads of polynomials with the same degree. For instance, you might contain loads of constant polynomials, in which case all of them have the same degree, which is 0. Just pick one of them in that case. So if there are loads with the same degree, just pick one of them. It does not matter. All I'm saying is you're not allowed to have as your smallest degree polynomial the 0 polynomial, unless you actually are the 0 ideal. Okay, but then you're a silly ideal. Okay, so for all other ideals, you can pick the polynomial of smallest degree, and as I say, if you've got degenerate options, just pick one of them. Okay, so you can always do this then, and I claim now that the ideal is going to be the principal ideal generated by P of x. Now, how am I going to do this? Well, to go further, what I now need to prove to you is that everything in this ideal is of the form, this polynomial of smallest degree, P of x, multiplied by some other polynomial in the ring of polynomials over the field, capital F. Okay, and the way I'm going to proceed forward is by proof by contradiction. So I'm going to say, let's say that there is some polynomial g of x here, which is not of this form. Okay, so let's say we have a g of x that is not of this form. It's not the polynomial p of x multiplied by f of x. I'm going to prove that I can contradict the fact that p of x was the polynomial of smallest degree. Okay, now how am I going to go about that? Well, I'm going to use effectively the equivalent of the Euclidean algorithm in the integers for this ring of polynomials over the field f. Okay, and the equivalent of the Euclidean algorithm in the integers for this ring of polynomials over the field f is that if you have any polynomial in the ring of polynomials over a field capital F, and you have another polynomial and you want to write this one as a multiple of p of x, then either you can do it perfectly. Okay, so any polynomial can either be written as a perfect multiple of my polynomial p of x, where this other polynomial q of x is just some quotient. Okay, so here is some arbitrary polynomial in the ring of polynomials over the field capital F. Here is the polynomial that I would like to write it as a multiple of. This new thing here, q of x, this is the quotient, okay? This is the thing I have to multiply p of x by to get g of x. Now either p of x, either g of x can actually be written perfectly as a multiple of p of x, in which case this is it, or it can't. And if it can't, then you're going to have to add on a remainder polynomial, r of x here. So this is the remainder, okay? And the important thing here is that the degree of the remainder of x will always be less than the degree of the polynomial p of x, which we're trying to use to divide the polynomial g of x. Okay, so this is the theorem then that we're going to have to explore and get some understanding of, because we're about to use it to prove this. Okay, this is the equivalent of the Euclidean algorithm in the integers for the ring of polynomials over the field f. Okay, and it says that if you have any polynomial g of x in the ring of polynomials over the field f, and you want to divide it by the polynomial p of x, then you want to write this polynomial as some quotient times p of x, and either you can do that perfectly, you can find a perfect quotient to perfectly make it so that q of x times p of x is equal to g of x, or you have to add on this remainder of x here plus r of x. But you can absolutely always do this, and if you do have to have a remainder term, the degree of the remainder term will at least be less than the degree of the p of x here that you were using to divide g of x by. Okay, right. So what we want to do is try and explore why this is true. Now, it's quite difficult to explain why this is true, and I think the best way to approach this is to firstly do an example to make this concrete, and then talk about it more abstractly, because talking about it more abstractly can get very, very confusing. Okay, so I think it's best firstly to do a concrete example of doing this, so that you're all familiar with exactly what we're doing here, because this isn't difficult. This is something that you will have done in the real numbers for a long, long time, okay, dividing one polynomial by another polynomial and getting a remainder. But I just want to do a concrete example and then discuss more abstractly for a more general field exactly why you can always do this. Okay, right. So firstly, let's do a concrete example from the ring of polynomials over the field of real numbers. Okay, so everyone's favourite field. So we're working with polynomials where the coefficients are in the real numbers. Okay, so firstly, let me give you g of x and a p of x. So I'll start off with the g of x. So I want to do not a totally trivial example, but not a too complicated example, so I'll come up with a cubic. Okay, so let's have the cubic 4x cubed, and I'm just making this up, plus, let's say, 3x squared, maybe we'll have a negative, minus 2x plus 1 there. Okay, so here is some polynomial where the coefficients are all in the real numbers, in the field of real numbers. Okay, now, what I want to do then is come up with my polynomial p of x, which I want to attempt to divide this polynomial by. Now, of course, p of x is going to have degree less than this if I want to attempt to write this one as a multiple of this one. Okay, so I'm going to make it a quadratic polynomial. Okay, so we'll have 2x squared plus, let's go for x plus 3 there. Okay, so there's a polynomial of degree smaller than it. And what I now want to do is write g of x as a multiple of p of x plus some remainder. Okay, so what I now want to have is I want to have my g of x, so I'll write it here, 4x cubed plus 3x squared minus 2x plus 1, written as some quotient polynomial, q of x, times my polynomial p of x, 2x squared plus x plus 3, plus some remainder polynomial r of x. So I want to find q of x and r of x. So let's start off with q of x. So what are we going to use as our quotient here? Well, this polynomial, what degree is it going to have? Well, I hope it's intuitively obvious that this polynomial needs to have degree 1, okay, because otherwise when we multiply these we're going to end up with something of a higher degree than 3 here. Okay, so what I'm going to do is I'm going to have a degree 1 polynomial, so it'll be something like this, q1x plus q2, and I'm going to multiply it by this thing here, 2x squared plus x plus 3. Okay, now, how is this going to work? Well, the highest degree term that I'm going to get out of this when I perform this multiplication is the q1x times this portion here, 2x squared. And in fact, what I might do is actually multiply this out explicitly. So the way, of course, that you will multiply this out is you'll multiply this one by all of these, and then multiply this one by all of these, and add them all together. So let's start with this one. You'll get 2 times q1x cubed plus q1x squared, so this one multiplied by this one, plus 3q1x, like so. Then multiplying this one by all of these, you'll get plus q2, whoops, missed a bit off there, plus 2q2, and then we'll get x squared, plus q2 times x, and then plus 3q2 there. Okay, so this is this thing that we'll get here. Now let's just collect terms with the same power of x together. So this will overall become 2 times q1 x cubed plus 2 times q2 plus q1 x squared plus 3q1 plus q2 times x, and then we'll finally have plus 3q2. Okay, now wouldn't it be wonderful if we could pick q1 and q2 such that all of these coefficients perfectly match those ones there? If such a q1 and a q2 exist, then we will be able to write our polynomial gx as a perfect multiple of our polynomial px. However, that's not always going to be the case. So what we will aim for is just trying to make these two first terms be equal to these two first terms here, and then we'll use the remainder x to make the final two terms work there. Okay, so what we'll then do is say, okay, we need 2 times q1 to equal 4 here. Okay, so we want 2 times q1 to equal 4. Now, of course, you can instantly say in the real numbers that the answer here is 2. But in a more general field, this is a very easy algebraic equation to solve. All we're going to do is multiply by the multiplicative inverse of 2 on both sides, and we'll then get that q1 is equal to the multiplicative inverse of 2, a half, times 4. And of course, a half times 4 is equal to 2. So that's why this can generalize into a more general field, because to work out the answers here, you're just doing field algebra. Okay, so q1 is going to have to equal 2 to make the first term here stack up, well, work at all. Now let's go to the second term. We already have q1 set, so we might as well now stick in our answer for q1 there. So we'll get 2 times q2 plus 2 as our answer for q1 now needs to equal this term here, so it needs to equal 3. So again, this is just an algebraic equation. We can do this in a general field. Yes, we're working in a very intuitive field, but we can do this in any old field. So what we're firstly going to do is add on to both sides the additive inverse of 2. So we'll get that 2q2 is equal to 3 plus the additive inverse of 2, which is of course equal to 1. And then what we'll do is multiply both sides by the multiplicative inverse of 2, and we'll get that q2 is equal to a half. Okay, so that now sets what q2 has to be equal to. Okay, so we now have q1 and q2 set, and as long as we make q1 and q2 equal to those two things in this quotient polynomial, so as long as we make this quotient polynomial, what was q1, 2 here, 2x plus a half, like so, then when this multiplies by our polynomial px here, then it will make the first and second terms correct. Now, let's think now what the final two terms will be when we set q1 and q2 equal to these two things. So this term here, so now let's substitute in q1 is equal to 2 here, we'll get 6 plus a half, so we'll get 6 halves here, so this will be 6 halves x, okay, and that's not equal to negative 2, so we haven't succeeded in making this term work. 3 times q2 is then 3 halves, and of course that's not equal to 1, so this term hasn't worked either. So we now have to put on the remainder, r of x here, to patch up the overall thing and make the overall thing now work. So this is going to have to be a degree 1 polynomial here, okay, so we'll put it in here as r1x plus r2, and r1 is going to have to add to 6 halves to give us the correct term here, and r2 is going to have to fix this term here to make it equal to that. Okay, so to write this out, r1 plus what I've got here, 6 halves, is going to have to equal negative 2, and r2 plus what I've got here, plus 3 over 2, is going to have to equal 1. Okay, and therefore I can work out what r1 and r2 are going to have to equal. So to just finish this off then now, r1 is going to have to equal negative 2 plus negative 6 over 6.5, okay, which will be negative 8.5. And r2 is going to have to equal 1 minus 3 over 2, which is just minus a half. Okay, so finally, our remainder polynomial here, r of x, is going to end up being negative 8.5 x plus negative a half. Okay, so there is our final remainder polynomial. Okay, so you have to find this quotient polynomial and this remainder polynomial so that this expression works out. Okay, and if you're very lucky, you might be able to find a quotient polynomial which will actually multiply with this to directly give you this, and then your remainder polynomial will be the 0 polynomial. Okay, so now let's go a little bit more general then. Let's take a step back and go back to our more abstract field setting. Now that we've seen a concrete example of what we're really doing here, and we understand what the quotient polynomial and the remainder polynomial actually are, let's think about why this is going to hold true in a more general field. Okay, so in a more general field then, we're going to have some polynomial g of x, the polynomial which we're trying to make as a multiple of p of x. Okay, and this is going to have degree higher than p of x. So let's say it's g0 plus g1x plus all the way up to, let's say, gn x to the n, where n is the degree of g. Okay, so this is our polynomial g of x here, and I'll underline that in green. Then we're going to have our polynomial p of x again, and p of x of course is going to have degree less than this. So it will be a polynomial of this form, p0 plus p1x plus all the way up to pm xm here, where m is the degree of p and therefore has to be less than, or I suppose equal to n. Okay, right, so here is p of x here. Okay, and what we now want to do is write g of x is equal to some quotient times p of x plus a remainder of x. Okay, so let's write this out. g0 plus g1x plus all the way up to gn x to the n here is going to have to equal some quotient. Okay, now what is the degree of the quotient going to be? Well, the degree of the quotient is going to have to be the thing that can multiply the degree here to take you up to the degree here. So it's going to have degree n minus m. Okay, remember the quotient here had degree 1. That was just the degree of this one, which was 3, minus the degree of this one, which was 2, which gives us 1. Okay, so n minus m is going to be the degree of the quotient, so we'll have q0 plus q1x plus all the way up to qn minus m, x to the power of n minus m, multiplied by our polynomial here, which will be p0 plus p1x plus all the way up to pm x to the m. And then we're going to have the remainder. Now, it will be our job to show that the remainder can be degree less than p of x. So I'll just leave the remainder at the moment as just r of x there, because we don't know what the degree of that is going to be yet. The big thing we want to show is that that's going to have degree less than the degree of p of x, less than m. Okay, so here's g of x, here is p of x, here is our quotient, and here is the thing that we're actually interested in investigating, the remainder term here. Okay, now, just like we did in our concrete example here, what you will do is you'll select, well, firstly I should say, the things that you have got free to manipulate are all of these coefficients here. Now, how many of those coefficients have you actually got here? Well, you might instantly say n minus m of them, but remember you've also got q0 here. So from q1 up to qn minus m, you've got n minus m of them, but you've also got that one. So overall you've got n minus m plus 1 things to play around with there, to set so that they can make as much of this as correct as possible. Okay, so just like we did in our concrete example, you will select qn minus m firstly, and you'll select it so that it multiplies by pm to give you gn here, the highest, the coefficient of the highest degree term in this polynomial gx. And because this is field algebra, you'll always be able to make this work. Okay, so you'll always be able to make it so that you can select qn minus m so that it will multiply with pm to give you gn, because of course you can always just take the multiplicative inverse of this, and we're assuming here that this is not equal to 0, because otherwise this wouldn't be the highest degree term. Okay? So you can always solve these equations. So you start by manipulating this equation and finding the answer for qn minus m. Okay, so you then set qn minus m, and that means that the first term here will be correct. And you then work down them and gradually make more and more of the terms here correct. Now, each one of these things that you've got here to manipulate will make another one of these correct, just like we did in the concrete example. Okay, so each one of these you'll be able to set, and you'll just work down them, and gradually as you set them you will make it so that all of that you make one of the terms here correct as well. Okay, so how many terms here will you overall be able to make correct? Well, you'll be able to make n minus m plus 1 of them correct, because you've got n minus m plus 1 of these coefficients in the quotient polynomial to manipulate. Okay, now, how many then are not free for you to manipulate? Okay, of course you can get the others right if you're very, very lucky, if this one truly is a multiple of p of x, but usually the others won't be under your control. Okay, so how many of those will be left that aren't under your control? Well, overall, how many coefficients have you got here? Well, you've got n plus 1 of them. Okay, so then what you're going to have to do is you're going to have to take away n minus m plus 1, and I'll just go over, I didn't explain fully why there's m plus 1 coefficients here. Well, of course, there's n from g1 to gn, and there's another one here. Okay, so now, how many of these have we set? We've managed to set n minus m plus 1 of them, so we'll subtract off n minus m plus 1 here. Okay, when we subtract off the n here, that bit will cancel with that bit, we'll get a plus m here, and then we'll get the 1's cancelling. So overall now, there is still n things to be set here. Okay, you're still wrong, usually, on m coefficients here. So now the remainder of x here is going to have to be the bit that makes the rest of that right. Okay, so what degree then does r of x need to be? Well, you might say r of x will have to be degree m, but you'd be wrong, because remember, r of x will be r0 plus r1. You've got to count this as something you can vary as well. Okay, plus r2 x squared. So actually you're only going to need to go up to rm minus 1, like so, because then you'll have m things which you can set here. 1 here, m minus 1 all the way up to here, so overall have m things to set here. Okay, so you only need your polynomial, your remainder polynomial, to be degree m minus 1. Okay, so the degree of r of x at the very maximum is going to have to be m minus 1, so it will be less than or equal to m minus 1. Okay, so i.e. it's always going to be strictly less than the degree of the polynomial p of x. Okay, so you can always take some polynomial in your ring of polynomials over a field capital F and write it as some quotient polynomial multiplied by the polynomial p of x plus a remainder polynomial which will have degree less than the degree of the polynomial p of x. Okay, right, so now we can turn back over to proving what we wanted to prove here. So I claim that it's very simple now to prove this, because we can do it by proof by contradiction. So we said, suppose there is some polynomial g of x here that is not, repeat, is not a multiple of our polynomial p of x. That means it is not a perfect multiple of p of x. So when we do this thing that we've just spent so long discussing, we will actually get a non-zero remainder here. We'll get some remainder term here, but we now know that the degree of that remainder term will be less than the degree of the polynomial p of x, and that causes a problem, because g of x is by assumption an element of our ideal. Q of x times p of x is an element of our ideal, because our ideal here contains all of the multiples of p of x. It has to, because p of x is an element of the ideal, and therefore any multiple of p of x has to be in the ideal. Okay, because ideals are closed under multiplication by any element of the larger ring. So that means that g of x minus, or rather plus, the additive inverse of q of x times p of x is an element of the ideal, because remember, the ideal is an additive subgroup. It's closed under addition. So I have some element of the ideal here. I've got its additive inverse there, and I'm adding that to g of x, another element of the ideal. So whatever this is, it must be in the ideal. But that's equal to this remainder term, r of x here. Okay, so that proves that r of x has to be an element of the ideal, but I've said that r of x has degree strictly less than the degree of the polynomial p of x. So now it contradicts p of x being the smallest polynomial in that ideal. Okay, so what I have just shown you is that if you find a polynomial of smallest degree here, the entire ideal has to be of the form the principal ideal of p of x, i.e. everything in that ideal has to be writable as a multiple of p of x, some element of the ring of polynomials over that field multiplied by p of x. Okay, if you assume that you have an element which isn't a multiple of p of x, it isn't a perfect multiple, then you can disprove p of x being the element of smallest degree in the ideal. You can prove that there was an element of smaller degree. Okay, so there's a proof by contradiction, which hence proves that all of the ideals in this ring of polynomials over the field capital F for any field are principal ideals, always, and the element that you can use to generate those principal ideals is merely the polynomial of smallest degree. Okay, and with that we will finish this video on fields and ideals.